In the previous lecture, we defined what a Euclidean domain is. We motivated the definition of Euclidean domain by showing that ring of integers and ring of polynomials over a field, both of them are PIDs, and we observed that the method of both of these proofs depend on a division algorithm. That motivated us to define a Euclidean domain, and let me quickly recall what it is. An integral domain is called a Euclidean domain whenever we have a norm function. A norm function is a function from our integral domain D to the set of non-negative integers, such that the only element that's sent to 0, the only element with norm 0 is 0. And moreover, we have a type of division property, meaning whenever I give you an arbitrary element A and a non-zero element B inside this integral domain, we can kind of divide A by B. That means what? That means we can find a quotient and a remainder inside this ring such that A is B times Q plus the remainder, and the reason that we call it a remainder is because its norm is supposed to be strictly less than norm of B. So notice that here we are not asking for Q and R to be unique. We are just asking about the existence of such elements. So whenever we have such a norm function with these properties, we call the a Euclidean domain. And the key reason that we defined such a thing was to show that every Euclidean domain is a PID. So this is what we showed in the previous lectures, that every Euclidean domain is a PID. And the last thing that we wanted to show was that the ring of Gaussian integers, meaning the ring that we get out of adding I to Z and making it into a ring, the smallest subring contains both Z and I, which consist of elements of the form A plus BI, where A and B, both of them are integers, is a Euclidean domain, and therefore it is a PID. So let's start with the proof of this statement. Why the ring of Gaussian integers is a PID. Okay, so this means we have to find a norm function. We have to define a function from the ring of Gaussian integers to non-negative integers with the properties that are mentioned, meaning the only element that's mapped to 0 is the 0 element, and we have a type of division property. Okay, let's start with the definition. It turns out that the definition to be norm of z squared, the complex norm of this complex number squared, does the job. So this is what we want to show. So we define the norm function on the Gaussian integers to be the complex norm squared. Let's notice that in this case, norm of an element of the form A plus BI by definition is A squared plus B squared, and when both A and B are integer numbers, this is also an integer, and because I am adding two perfect squares, this is definitely a non-negative integer. So it is indeed going to the codomain as promised. The other thing that we notice is that a complex norm of a complex number is 0 precisely when it is the 0 complex number. Or alternatively, you can again look at this equation and see that because I'm adding two squares, both of them are non-negative, the only scenario that we can end up getting 0 is when both A and B are 0. So we definitely have this property. Let's go to the more important part, meaning why do we have this type of division property of a Euclidean domain? Okay, so it means what? I am going to give you a pair of elements, A plus BI and C plus DI, inside the Gaussian integers, with the assumption that C plus DI is not 0, and we want to show that we can find a quotient and a remainder. So what we will do is that we start with division within complex numbers. So Z and W, both of them are complex numbers, and W is a non-zero complex number, and therefore I can talk about Z over W as a complex number. So this is a complex number. So similar to what we do in the integers. What do I mean by that? So whenever I give you two integers, one way of thinking about a quotient is by saying that I'm looking at the fraction m over n, and then I'm getting some integer, some real, also in fact rational number, but definitely some real number. And then what we can do, the way that we can think about the quotient, at least when so in fact anyway, I mean, regardless of the sign of m and n, is by looking at the tiling that integers give us. So we have 0, 1, and so on. And then the quotient is nothing but the integer part of this fraction is precisely the quotient. Or alternatively, what I'm saying is that we are taking this tiling and then we are shifting every real number by some integer in order to get into this red interval. So I want to use this kind of geometric tiling of integers in order to understand the quotient, because this type of geometric understanding and tiling is what can help us to understand Euclid property for other rings such as Gaussian integers. So z divided by w as a complex number gives us a point in the complex plane. Now, when I look at the points that are given to the Gaussian integers, we get this grid. We get the lattice of points that are coming from the Gaussian integers that I'm going to denote by these red dots that we have over here. So these red dots are coming from the Gaussian integers. Now, for every one of these points, I can ask myself what points in the plane, are closest to this particular dot. For instance, if I start with the origin and I ask myself what points on the plane are closest to the origin compared to the other Gaussian integers, we end up getting this blue square in the middle. Or in general, I can look at the shifts of this blue square and end up getting this kind of tiling for the plane, tiling by squares. So this one, and so on. So we end up getting this tiling for the plane, for the complex plane. And this tiling can help us to say that every point on this plane can be shifted by some Gaussian integer, and by a shift of Gaussian integer, we can make it and put it inside the blue square in the center, in the middle. Okay, so I can use a shift by Gaussian integers in order to put every point on the plane in the square in the middle. Okay, so let's in this square. What does that mean? This means that, let's say I look at the fraction z divided by w, that's a complex point. I can definitely find some lattice shift, some integer Gaussian q, such that the difference between this complex number and this Gaussian integer belongs to this middle square, and that means that it belongs to this interval times the other one. So the real part is within the range -½ to ½ and the imaginary part is also within the range -½ to ½ That means in particular that the norm, the complex norm of this difference cannot be more than half of the diameter, diagonal of this square, and that means that this difference is definitely at most √2 divided by 2. Now, if I multiply both sides of this inequality by norm of W, we end up getting that the absolute value, the complex norm of Z minus Q times W is at most root 2 divided by 2 times norm of W, and because root 2 divided by 2 is a number less than 1, this is strictly less than norm of W. Now, notice that Z minus QW, Z and Q and W, all of them are Gaussian integers, and Gaussian integers form a ring. Therefore, Q times W is a Gaussian integer. Therefore, Z minus QW is also a Gaussian integer. That means R, which is Z minus QW, this is how I'm defining R, this is also a Gaussian integer. Now, by this choice, let's summarize what we've shown. We showed that Z is QW plus R for some Q and R that are Gaussian integers. So here, Q and R, both of them are Gaussian integers. And we also, in fact, showed over here in this inequality, we showed that norm of R is strictly less than norm of W. And these are exactly the properties that we were looking for. We ended up finding a quotient-ary remainder that satisfies the Euclid domain property. So that means that the ring of Gaussian integers is a Euclidean domain, and therefore, because every Euclidean domain is a PID, that implies that the ring of Gaussian integers is a PID. Okay, so in fact, in your homework assignment, you show that the same technique, you can use the same technique, and you do that in order to show that the ring, the smallest ring that contains the third root of unity, which is this omega, and the real part of omega is -½ and the imaginary part is root 3 divided by 2. This is precisely the third root of unity. Let me see. So if this is the unit disk, and these are the axes, the real axis and the imaginary axis. Then this point omega, okay, so this is 1, and then I have omega over here. This is the third root of unity. So if I square omega, I get omega squared, and then I raise it to power 3, I get that it is precisely 1, and that's why I call it the third root of unity. Okay, so whenever I add omega, the third root of unity, to Z, and get the smallest ring that they generate, that's denoted by Z bracket omega, then we can show that every element inside the ring is of the form A plus B omega, where A and B, both of them are integer numbers. And one can use the same technique as we just showed for Gaussian integers and show that this is in fact a PID. In fact, you show that this is a Euclidean domain, and then from there we can deduce that this ring is also a PID. And this, let me just mention it, it's not that easy, but one can use this and show a particular case of Fermat's last conjecture, which is the case where you want to show a to power 3 plus b to power 3 can never be c to power 3 unless one of them is 0. The proof is not very easy, but it's something that Fermat could do. Okay, so let's go back to zeros of polynomials. So we discussed the Euclidean domains, and that was kind of generalization of the method that we showed. Every ideal of a ring of polynomials over a field is principal, but let's go back to ring of polynomials and try to understand zeros of polynomials. So this is a common thing. We often go and find a common theme define certain things for various ring, commutative rings often, or integral domains. But then come back to ring of polynomials. Okay, so we want to understand zeros of polynomials. So let's talk about zeros of polynomials, meaning we say a complex number is algebraic if it is zero of a polynomial with rational coefficients, a non-zero polynomial, of course. So a complex number is called an algebraic number if it is zero of a polynomial with rational coefficients. And of course, I have to assume that the polynomial is not zero, otherwise every complex number would be. Okay, so again, a complex number is called an algebraic number if it is zero of a polynomial with rational coefficients. In fact, we can make it a bit more general. What do I mean by that? So suppose I give you any field, it doesn't matter if it's Q or not. Right? So I give you a field F. So in the first part of the definition, this F was like Q, and I give you another field that contains this F. In the first part of the definition, it was just complex numbers. Okay, suppose I'm giving you a field E that contains F as a subfield. In this case, we often say that E is a field extension of F. So we say that E is a field extension of F. Okay, so suppose that I have this field extension, then an element inside this larger field is called algebraic over F. So we say alpha is algebraic over F. So I need to specify F as well. So we say alpha is algebraic over F if alpha is a zero of a polynomial with coefficients inside F, a non-zero polynomial with coefficients inside F. If this is the case, then we say alpha is algebraic over F. So when instead of saying alpha is algebraic over Q, we can just simply say that alpha is an algebraic number. But in general, we have to specify and say alpha is algebraic over this field F. Examples. So, for instance, the third root of 2 is an algebraic number because it is a zero of the polynomial x to power 3 minus 2. And x to power 3 minus 2 is a polynomial with rational coefficients. Therefore, it is an algebraic number. Now, in order to specify that here, it's important that E is something that's most likely larger than F. Let's emphasize that over every field F, every element of that field is algebraic over it. So let me repeat what I'm saying. So suppose F is a field, and I give you an arbitrary element, small a, inside this field. Then this is automatically algebraic over the same field F. So A is algebraic over F. Why? Because it is a zero of the polynomial x minus a. So this means being algebraic is interesting only when we go to some field that is smaller. So every element of the field F is algebraic over F. Every element of Q is algebraic over Q, but not every element of complex numbers is algebraic over complex numbers. In fact, this is not easy, but one can show that, so let me give you a non-example. One can show that pi or the Euler number E, they are not algebraic numbers. They are not algebraic over rational numbers. They are not algebraic numbers. They are not algebraic. So E is slightly easier than pi, but we can show both of them. They are, they need their own technique. I mean, we don't have time to go into the proof of them. But just to let you know. In fact, using cardinality arguments and set theoretic argument, one can show that in some sense, most of elements of complex numbers are not algebraic. So in fact, the set of algebraic numbers is a countable set. There is a bijection between them and a ring of integers, but there is no bijection between the set of complex numbers and real numbers and set of integers. So there are much more numbers that are not algebraic. But if you give me a concrete number and ask me, can you show that this number is algebraic or not? This is actually a rather hard question. Okay, so again, let's repeat. A number is called algebraic over a field f if it is zero of a non-zero binomial with coefficients inside f. Let's try to understand this in terms of evaluation map and terms that we've learned about ring homomorphisms. So if you think about it, evaluation map, we've discussed the evaluation map from ring of binomials with coefficients inside f to the larger field E is a ring homomorphism. And what is the kernel of this? The kernel of this evaluation map consists of those polynomials that have alpha as a zero. So if we say alpha is algebraic over f, it's the same as saying that kernel of the evaluation map is not the zero ideal. So vice versa, if the kernel of the evaluation map is not zero, this means I can find a polynomial there that has alpha as a zero. And if it is zero, then we don't have such polynomial. So this means alpha is algebraic over f precisely when the kernel of the evaluation map is not zero. Okay, so this is a modern way of understanding algebraic numbers. But let's see, at the end of the day, we want to understand these algebraic numbers, do arithmetic with them, add them, multiply them, and so on. This means what? This means we want to understand the ring structure of f square bracket alpha, or in the case of rational numbers, q square bracket alpha. This is what we want to do. This is a good part of this course. By the first isomorphism theorem, we do know that the ring of rational numbers modeled by the kernel of the evaluation map is definitely isomorphic to the image, and the image is what we denoted by q bracket alpha. So this means if I want to understand the ring structure of q bracket alpha, I need to understand the kernel of the evaluation. Okay, that's one thing. Another thing that we see immediately out of this is that as soon as alpha is not an algebraic number, so in that case, the kernel would be the zero ideal, and the quotient by the zero ideal is isomorphic to the ring itself. So we immediately get that if alpha is not an algebraic number, then the ring that we get out of adding alpha to q is nothing but the ring of polynomials with coefficients inside q. It's isomorphic to the ring of polynomials with coefficients in q. So this means this ring might have complicated structure only when alpha is an algebraic number. And in that case, we want to describe elements of this ring. We want to understand the ring structure. So in a sense, is it an integral domain? That we know because it's a subring of complex numbers. Is it a field? In fact, in all the examples that we've seen so far, such a thing is a field. And we want to show that this phenomenon is true for every algebra. Again, let me repeat that we've seen, so notice that we've seen that q joint I, q joint root 2, and so on, but they are all field. And this is what we want to show in general. We want to show that q bracket alpha, when alpha is an algebraic number, is always a field. Okay, so this is what we want to generalize. And as we see over here, because of the first isomorphism theorem, the starting point would be understanding the kernel of the evaluation. Okay, so we do know that the kernel is principal. Why? Because kernel of the evaluation map is an ideal of the ring of polynomials with coefficients in a field. And we know f bracket x, whenever f is a field, is a PID. This means every ideal is principal. Now, we take this generator and we want to understand properties of this generator. Okay, so let's make it formal. So suppose I give you a field extension. So suppose E is a, suppose E is a field extension of F. And suppose I give you an element of this larger field that is algebraic over the smaller field. Okay. Now I want to describe, you want to get a better understanding of the kernel of the evaluation map. And the statement says this, that there is a unique monic binomial. Monic means the leading coefficient is 1. Okay, so let me write it over here. This means leading coefficient is 1. So there is a unique monic binomial with coefficients inside f that we denote by m sub alpha. Because it's unique, I can denote it by notation. It's fixed. It depends on alpha and f, but I'm not writing f here, but it does depend on f. So there is a unique monic binomial with coefficients inside f with the following properties. What is the property? It is a generator of the kernel. So kernel is generated by a monic binomial, and this monic binomial is unique. There is a unique binomial, unique monic binomial that generates kernel of the evaluation. Moreover, the more important part of this, that if I take this binomial m sub alpha, this is a non-constant binomial with this property, that it cannot be written as a product of polynomials that have smaller degree. So this m sub alpha cannot be written as a product of a smaller degree polynomials in f bracket x. Okay, this is a crucial part of this generator. We call this generator the minimal polynomial of alpha over f. So this unique binomial that we denoted by m sub alpha, or sometimes I write m sub alpha comma f when I want to emphasize that this guy belongs to f bracket x. So the unique minimal polynomial of alpha over f has what property? It generates the kernel of the evaluation map, and it is monic, it is not constant, and more importantly, it cannot be written as a product of two polynomials of a smaller degree, where both of these polynomials belong to f bracket x. Okay, so this is what we want to show. Let's start by showing the existence. So again, because f is a field, we have already proved that f bracket x is a PID. Every ideal is principal. In particular, kernel of the evaluation map is principal ideal, which means it is generated by some polynomial. So suppose it's generated by a polynomial p. Now, because alpha is an algebraic number, we know that's the same as saying that the kernel is not 0, which is the same as saying that this polynomial is a non-zero polynomial, and therefore the leading coefficient is not 0. So a sub n is a non-zero element of the field f. But f is a field, so every non-zero element is a unit. That means I can multiply by its inverse. So that way I can get a monic binomial inside f bracket x. So p bar I denote it to be the inverse of the leading coefficient times p of x. So I get a monic binomial inside f bracket x, and more importantly, this polynomial, this monic binomial, belongs to the ideal generated by p because it is a multiple of p of x. Now, conversely, Because P of x is a multiple of P bar, we deduce that the other way around. P belongs to the ideal generated by P bar. Now, P bar, the ideal generated by P bar was a subset of ideal generated by P because P bar was a multiple of P. Now, P is a multiple of P bar, therefore the ideal generated by P is a subset of the ideal generated by P bar, so they are the same. That means I found a monic polynomial P bar where the ideal generated by that guy is the kernel of the evaluation. So this shows the existence. So we found a monic polynomial that generates kernel of the evaluation. Now I want to discuss the uniqueness. What do I mean by that? So suppose there is another polynomial. In fact, this we show in a more general setting. What do I mean by that? Suppose I tell you that P1 and P2, both of them are monic polynomials. And I tell you that both of them generate the same ideal. So if I give you two monic polynomials that generate the same ideal, then they are the same polynomials. This is what I want to show. So in particular, this shows that there is a unique monic polynomial that generates kernel of the evaluation now. Okay, so why is that? Because when I assume the ideal generated by P1 is the same as the ideal generated by P2, from there I can deduce that P2 is a multiple of P1. That means this. And because the ideal generated by P1 is the ideal generated by P2, I can also deduce that P1 is a multiple of P2. This means this, that for some Q1 and Q2 inside the ring of polynomials over F, I can write down these equations. Now, when I compare the degrees of both sides, from here, I deduce that degree of P1 plus degree of Q1 is degree of P2. But here, degree of P2 plus degree of Q2 is degree of P1. And notice that these are non-zero polynomials. Therefore, that implies degree of P1 should be degree of P2. Okay, so in particular, this from here we can deduce again by comparing the degrees, we get these equalities, and because these are non-zero polynomials, the degrees always are non-negative, therefore the degrees are the same. Now that the degrees are the same, I can deduce that degree of Q1 should be actually 0, which means it's a constant, it is a non-zero constant. It's a non-zero constant, and let's call that non-zero constant C. That means what? That means that I can write down this product as CP1, but that is supposed to be P2. Now, if I compare the leading coefficients of both sides, the leading coefficient of this side is C, because the leading coefficient of P1 is 1. P1 is a monic polynomial. And the leading coefficient of P2 is 1 because it's a monic polynomial. So we end up getting that this constant C should be 1, which means P2 is P1. Is C times P1, and C is 1, therefore it is P1. And this implies the uniqueness of monic polynomial that generates kernel of the evaluation now. Therefore, we can talk about the minimal polynomial of an algebraic number. Now let's show the moreover part. So what was it? And we want to say that the minimal polynomial of an algebraic number is a non-constant polynomial. That part is not very hard, I will discuss, but the part that's more important is the following, that it cannot be written as a product of the smaller degree polynomials in f bracket x. This is the key thing that we want to show. Okay, so we have already argued that it's not constant because the constant polynomial, a non-zero constant polynomial, when I evaluate it at alpha, I can never get 0. So it cannot be constant. So m alpha is not constant. Okay, so now what? Why can't I write it as product of two polynomials in f bracket x that have a smaller degree? Suppose to the contrary that I can actually do it. So this means Now I can write down the minimal polynomial m sub alpha as a product of h, g, and h, where degree of both of these binomials are strictly less than degree of the minimal polynomial, and both of them belong to f bracket x. So this is the contrary assumption. Okay, now where does the contradiction come from? We are going to evaluate the equation that we had. We are going to evaluate this. We are going to substitute alpha for x. We are going to evaluate it at alpha. Because m sub alpha is in the kernel of the evaluation map, we do know that m sub alpha at alpha is 0. That means g of alpha times h of alpha should be 0, but g of alpha and h of alpha belong to E, and E is an integral domain. It is a field, therefore it's an integral domain. And therefore, either g of alpha should be 0 or h of alpha should be 0. This means either alpha is a 0 of g, or alpha is a 0 of h. That means either g is a multiple of the minimal polynomial, or h is a multiple of minimal polynomial. In either case, we get that either degree of g is more than, not in either case, if g is a multiple of m sub alpha and it's a non-zero multiple, we deduce that degree of g should be at least degree of the minimal polynomial. Similarly, in the other case, we deduce that degree of h should be at least degree of the minimal polynomial. But this contradicts the assumption that we had that both degree of g and degree of h are strictly less than degree of the minimal polynomial. So we reach to a contradiction, and this gives us this important property of the minimal polynomials, that they cannot be written as product of two smaller degree polynomials in f bracket x. In fact, this criterion, this condition can characterize minimal polynomials, and this will help us to find minimal polynomials of a given algebraic number alpha. Okay, so let's formulate and prove the converse of this moreover part. So again, the assumption is that we are given a field extension, and we are given an algebraic number over f. So alpha is algebraic over f. Now we want to formulate the converse. What does that mean? I'm going to give you a polynomial that is non-constant and monic in f bracket x. Now this polynomial is the minimal polynomial of alpha precisely when alpha is a 0 of p, and p cannot be written as a product of a smaller degree polynomials in f bracket x. So we have already discussed this direction, that if I give you the minimal polynomial, then it cannot be written as a product of a smaller degree polynomials in f bracket x. This part we have already discussed. The question is the other way around. So if I give you a monic non-constant polynomial that has alpha as a 0, and it cannot be written as a product of a smaller degree polynomials, how can I deduce that it is the minimal polynomial of alpha? We have seen arguments similar to this, a particular case of these things during the discussion and problem session in the past week. But let's repeat the proof in this generality. Because p of alpha is 0, that's part of our assumption, that implies that it does belong to the evaluation, to the kernel of the evaluation. But the way that we chose and defined the minimal polynomial kernel of the evaluation map is generated by the minimal polynomial of alpha over f. Okay, that means what? That means this polynomial p is a non-zero multiple of the minimal polynomial. When it is a non-zero multiple of this minimal polynomial, the degree of p should be at least degree of q. Okay, it is degree of q. And in fact, what we have is that P is Q of X times M alpha of X. It's a multiple of that. But by assumption, P is not supposed to be, we should not be able to write down P as product of two polynomials in F bracket X, where both of them have degree strictly less than degree of P. Okay, so now let's try to understand. P cannot be written as product of two polynomials of a smaller degree, and M sub alpha is not constant. So this means on one hand, degree of P is at least degree of M alpha. On the other hand, degree of P cannot be more than degree of M alpha. So again, let's write down what I am saying. I know that P of X is a multiple of M sub alpha. This is what we get from the fact that M sub alpha generates this. But then I cannot write down this as product of two polynomials of a smaller degree. And this is non-constant, so therefore its degree is not 0. From here, I deduce the degree of Q should be 0, and degree of P is precisely degree of M sub alpha. And therefore, Q just a constant. Okay, so Q is constant. Therefore, I have this equality for a constant Q. But again, the same technique. We are going to compare the leading coefficient of P with the leading coefficient of the other side. P is monic. M sub alpha is monic. The leading coefficient of the other side is going to be C, the right-hand side. And the left-hand side is 1. So altogether, we deduce that this constant C should be 1, which means this polynomial P is precisely the minimal polynomial of alpha over F. And that finishes the proof. That shows that a monic non-constant polynomial is the minimal polynomial of alpha precisely when alpha is a 0 of this polynomial, and this polynomial cannot be written as a product of two polynomials of smaller degree. Okay, so not bad. We have a sort of a characterization of minimal polynomial. Let's also point out that we can understand this minimality in terms of just degree. So meaning among all the polynomials that have alpha as a 0, the smallest degree among all the non-zero polynomials that have alpha as a 0 is precisely degree of the minimal polynomial. So let's formulate this precisely and write it in form of a proposition. So suppose E is a field extension of F, and alpha is an algebraic number over F. So it's algebraic over the field F, over the smaller field F. Then first of all, a polynomial with coefficients inside F has alpha as a 0 precisely when it's a multiple of the minimal polynomial. Okay, so it's a multiple of the minimal polynomial if and only if f of alpha is 0. And moreover, if I give you a polynomial with coefficients inside F that has alpha as a 0 and degree of every other polynomial that has alpha as a 0 is at least degree of this polynomial. So this means what? Again, degree of P, this polynomial that I'm giving you, is the smallest one among non-zero elements of the kernel of the evaluation. If I give you such a thing, then it is precisely a scalar multiple of the minimal polynomial. So there exists some non-zero element of the field where this polynomial P is C times M sub alpha. So M sub alpha is more or less up to a non-zero scalar multiplication is the only polynomial of the smallest degree that has alpha as a 0. Okay, this is what we want to show. Let's do that. The first part is actually straightforward from the fact that M sub alpha generates a kernel. So f of alpha is 0 precisely when it belongs to the kernel of the evaluation. But kernel of the evaluation map is generated by the minimal polynomial of alpha over f. And that means that that happens precisely when f is a multiple of the minimal polynomial. So this shows the first part. Now let's go to the second part. So because alpha is a 0, that implies alpha is a 0 of p, that implies that, okay, let me go this way first. Because m sub alpha is 0, m sub alpha of alpha is 0, by this condition, by the second condition, by this condition, we know that if any polynomial, any non-zero polynomial has alpha as a 0, then its degree should be at least degree of p. So because m sub alpha of alpha is 0, we deduce that degree of m sub alpha should be at least degree of p. So this is one lower bound. But let's go back to main property of minimal polynomial. Minimal polynomial generates the kernel, the evaluation kernel of the evaluation map. And we are told that p of alpha is 0. This means p does belong to the kernel of the evaluation map. So I do have that p of alpha is 0, and therefore p belongs to the kernel of the evaluation map, which means it's a multiple of the minimal polynomial. And so the degree of this p should be at least degree of the minimal polynomial. If I compare these two, I deduce that they have the same degree, and now it's easy because it's a multiple of the other one and they have the same degree. This means that it should be scalar multiple of the other one, and claim follows. If you think about it, it's not very hard. So again, it's all based on degree. Okay, so now we have very good understanding. So relatively good understanding of the kernel is generated by this minimal polynomial. This minimal polynomial has this property that it cannot be written. It's a non-constant polynomial that cannot be written as a product of polynomials of a smaller degree. And f brackets alpha is isomorphic to this quotient ring of polynomials by the minimal polynomial. So now there are two questions. Can we actually understand this? Can we use this property? Can we use this property and pinpoint the minimal polynomial of a given algebraic number? This brings us to the definition of irreducible elements, and we'll get to this later. And this part brings us to this question: can I describe elements of this quotient ring? Okay, let's start with this one because this is an immediate corollary of division algorithm. So we are given a field F, and I look at the ring of polynomials. I give you a non-zero polynomial, in fact, non-constant polynomial. So suppose that the degree is n, which is at least 1. Then every element of the quotient ring has a unique form, has a unique representation that's given by a polynomial whose degree is strictly less than n, strictly less than degree of p. So this representation is unique, and everything can be represented of this form, and it is unique. So this is what we want to show. Let me finish proof of this proposition, and then we'll continue the rest in the next lecture. So this is immediate corollary of long division. So for a given polynomial p, we can divide this p by the polynomial p, and we get a quotient q and a remainder r. So we get a quotient q and remainder r. That means what? That means f is p times q plus r, and r has degree strictly less than degree of p, which means it is of the form a sub 0 plus a sub 1x the dot a sub n minus 1 x to the power n minus 1. Now, from the first equality, we get that f minus the remainder is a multiple of p, and therefore it is inside this ideal, which means the coset that's represented by f is the same as the coset that's represented by r. Okay, not bad. This means I'm showing that every element inside the quotient ring is of the form a polynomial of degree strictly less than n plus, the coset that's represented by a polynomial that has degree strictly less than n. So this shows existence. This shows that every element of the quotient can be written of this form. Now, let's talk about the uniqueness. This means I'm going to assume that I am given two representation of the same coset by polynomials that have degree strictly less than n. Let's call coefficients of the first one a sub i's and coefficients of the second representative by a sub I primes. I want to show that a sub i's are a sub I primes. So knowing that these cosets are the same is equivalent to saying that the difference between these representatives belong to this ideal, which means it's equivalent to say that their difference is a multiple of the polynomial p. But notice that this is a polynomial whose degree is at most n minus 1, and p is a polynomial of degree n. The only multiple of a polynomial of degree n that has degree at most n minus 1 is the zero polynomial, which means all the coefficients are 0, and this finishes the uniqueness. So we'll continue in the next lecture.